Hey everyone, and welcome. Think of this as a personal training session for your physics brain. We're going to dive deep and tackle 3 classic problems from the grade 12 model exam, all to get your problem-solving muscles seriously sharp. You ready? Let's jump right in.
And hey, this is not a spectator's sport. I really want you to try these along with me. So go on, grab a pen and some paper, and let's see if you can crack these problems before I do. Let's kick things off with challenge number 1. So our first challenge is a classic you've probably seen a million times, a complicated-looking DC circuit. I know, these diagrams can look like a tangled mess, but trust me, they're really just puzzles waiting for us to solve them. Okay, here's our circuit. We've got a 9-volt battery that's powering this whole web of resistors. The big question is, out of these 4 statements about the current flowing through it, which one is actually correct? All right, this is where you come in. Go ahead and hit that pause button. Sketch this out and work through it. See what you come up with. No rush, I'll be right here when you're ready to check your answer. Okay, you back? Awesome. So how in the world do we attack a monster like this? Well, our secret weapon is a concept called equivalent resistance. The whole game plan is to take this complex circuit and methodically simplify it down into one single equivalent resistor. Once we have that, finding the total current is easy. So we start by looking at the whole thing. And here's the golden rule for these types of problems. You always start at the part of the circuit that's farthest away from the battery, and you work your way back towards it, simplifying as you go. So let's make our first move way over on the far right. See that 2 ohm and 4 ohm resistor? They're in series, so we can just add them up. Easy, that gives us 6 ohms. Now, that new 6 ohm resistor is sitting in parallel with the 2 ohm resistor right next to it, so we combine those. And that's pretty much the entire strategy. We just rinse and repeat that process. We simplify a parallel branch, add it to the next resistor in series, and do it all over again until there's nothing left but one single resistor. If you work through all the math, the total equivalent resistance for this entire circuit comes out to a nice, clean 8 ohms. And from there, it's just good old Ohm's law. Current equals voltage divided by resistance. So we take our 9 volts divided by 8 ohms, and we get a total current of 1.125 amps. Now look where that 3 ohm resistor is. It's on the main path, right after the battery. That means it gets the entire fire hose of current, and that makes B our answer. If you got that, seriously, fantastic job. All right, let's totally switch gears for our second challenge. We're going to move away from a big calculation and into a more conceptual problem. This one really gets to the heart of what electrical resistance is all about. So here's the puzzle for you. We've got a copper wire, and our goal is to slash its resistance down to just 1/4 of what it was. But there are rules. Its length and temperature are locked in. We can't change those. We can only play with its physical shape. So what do? You know the drill by now. Hit pause and really think this one through. This is less about number crunching and more about understanding the relationship between a wire's dimensions and its resistance. The formula is definitely your best friend here. Okay, let's break this down. It all comes back to one key formula. Resistance equals resistivity times length, all divided by area. Now, the problem told us that resistivity and length are constant, so we can ignore them. This means resistance is simply inversely proportional to the cross-sectional area. In other words, a fatter wire means less resistance. But here's the crucial trick. The area of that wire depends on the square of its diameter. That little square changes everything. And this chart really lays it all out. Let's just look at option B. If we cut the diameter in half, that squared relationship means the area shrinks to 1/4 of what it was. And since resistance and area are inversely related, the resistance actually goes up by 4 times, the exact opposite of what we want. But now, check out option C. If we double the diameter, the area quadruples, which means the resistance drops down to exactly 1/4. Bingo! And that's our answer. Option C is the way to go. It's all about remembering that powerful, non-obvious squared relationship between diameter and area. Really nice work if you sniffed that one out. Okay, for our third and final challenge, we are taking a big leap into the world of modern physics. We're going to look at what happens to tiny little electrons inside a cathode ray tube. So here's the situation. We're accelerating electrons with a voltage. The question is, if we crank up that voltage to 4 times its original value, what happens to the final speed of those electrons? Is it a simple relationship? Does the speed also go up 4 times? Or is something else going on? All right, this is the last one, the grand finale. Give it a pause and give it your absolute best shot. Think about the energy involved. The key to unlocking this problem is one of the most powerful and fundamental ideas in all of physics, the conservation of energy. You can't just create or destroy energy, you can only change its form. And that's exactly what's happening here. The electrical potential energy the electron gets from the voltage gets converted one for one into kinetic energy, the energy of motion. So how does that look with the math? Well, when we set the potential energy equal to the kinetic energy, we find something really interesting. The speed squared is proportional to the voltage, which means the speed itself is proportional to the square root of the voltage. So if we multiply the voltage by 4, we have to take the square root of 4 to see the effect on the speed. And the square root of 4 is, of course, 2. The speed is simply doubled. It's not a direct linear relationship. It's that sneaky square root relationship again. So the correct answer is B. Absolutely brilliant if you nailed that final challenge. So we just chewed through 3 really different problems. We did circuits, material properties, modern physics, but you know what? The strategies we use to beat them are totally universal. So let's take a step back and really lock in our problem-solving toolkit. This right here is the real gold. For any problem you face, first just stop and ask, what's the big physics idea they're testing here? Is it energy? Is it resistance? Then break the problem down into bite-sized chunks, just like we did with that circuit. Visualize it, draw it out if you have to. And don't just memorize formulas, master the relationships within them, like that squared effective diameter. Finally, always do a quick gut check. Does my answer even make sense in the real world? And that's the real question I want to leave you with. How can you take this toolkit and apply it to everything else? Because it doesn't matter if you're looking at magnetism or waves or thermodynamics, this exact same strategic thinking works every single time. Keep practicing it and you will be ready for anything. Thanks so much for working through these with me today.